Hi, my name is Annie Tackett, and today I'm going to show you guys the steps of skeletal muscle contraction from prior to during the actual contraction of the muscle. My friend Tasha is going to do the second part, and I will do the first part. Let's do it! So first I will draw out the neuromuscular junction. So right now I'm going to draw the neuron. So right here you have this big soma, or this is the cell body, and then I'm going to draw the dendrites coming off of it. I'm not going to take too much time drawing these, but just know that the message from the presynaptic neuron has now sent the message to this postsynaptic neuron that is going to deliver, let's see if it'll focus, that's going to deliver the message to the skeletal muscle. Then here is the cell, or the axon, which is going to branch off into other places, but also we're going to close-in it up on this big synaptic knob. I'm just going to draw it like that. So that's our synaptic knob so far. And then down here is going to be our motor end plate. Okay, so the action potential is going to arrive and trigger these calcium channels to open. These voltage-gated calcium channels. So there's tons of calcium out here. And so these calcium channels are going to open up and allow this calcium to actually come inside the synaptic knob. So in the synaptic knob, there are tons of little vesicles filled with the neurotransmitter acetylcholine. So here are the vesicles filled with acetylcholine. So once the calcium rushes in, the calcium triggers these synaptic vesicles to bind basically to the membrane. So they're gonna exocytose, if that's the word, outside of the cell into this area right here, which is the synaptic cleft. So once this acetylcholine is in the synaptic cleft, it binds to these receptors on the motor end plate. So these are the receptors right here that the acetylcholine is actually binding to. Alright, so after this acetylcholine binds to the motor end plate, it allows, or more channels down here to open, which these again are voltage gated channels because the binding of the ACH triggers these chemically gated channels to open. This is called the end plate potential. One, because the potential of the membrane, resting potential, changes, and it's called end plate because it happens at the motor end plate. So these channels open, which allows the sodium out here, to rush inside the cell, again through these channels, and then we have potassium in here as well, which then slowly goes outside of the cell. So again, that is creating the end plate potential. So I'm going to draw on our little skeletal muscle here. So we have, I'm going to take a different color. We have these T-tubules that come in, which again are like deep invaginations of the sarcolemma. So we have these deep vaginations, which are the T-tubules, and then This right here is our sarcolemma. So I'll draw a little arrow. Sarcolemma. And we also have the sarcoplasmic reticulum in here as well. So let me just quickly draw that out. So this reticulum houses calcium inside of it at this terminal cisternae, which is this portion. This area right here is the terminal cisternae of the sarcolemma, sarcoplasmic reticulum. So once this end plate potential is caused by the acetylcholine, the action potential travels down the sarcolemma and into the T-tubule. So once the action potential does travel down to the T-tubule, once it travels down here enough where it reaches the sarcoplasmic reticulum, it triggers the opening of more voltage-gated calcium channels to release from this sarcoplasmic reticulum. So this calcium is being released from here. So this all is the basically first kind of half of the skeletal muscle contraction. So to review, we just had the action potential come down. It triggered these voltage-gated calcium channels to open, which triggers the synaptic vesicles, which are filled with acetylcholine, to fuse with this membrane and release the acetylcholine into the synaptic cleft right here. So once released, the acetylcholine binds to the receptors, which causes more voltage-gated channels to open. So sodium then rushes in, and then potassium slowly goes out, which creates this end plate potential. So it depolarizes the membrane, which causes, again, an action potential, and it runs down the sarcolemma into the T-tubule, which then in turn, once it reaches the sarcolemmic reticulum, triggers these calcium channels to open and calcium is released. So Tasha will explain the rest to you guys. I hope you learned a lot from this video, and see you later.
Hi, I'm Natosha, and I'm going to explain the sacromere and the contraction today, with Annie doing the first part and I'm doing the second part. Let's go! So for Crossbridge Cycling, it takes place in the sacromere, which is this, and the Ca2+ bindings, and the calcium binds to the tropin, and the tropin changes shape, moving the tropin tripomycin complex. The tripomycin complex is no longer covering the myso-binding site. Then the crossbridge formation, which is the attachment, is the cocked myosin head binds the actin. The power stroke pulling the myosin head pulls towards the center of the sacromere, called the power stroke, making the contraction. The release of the myosin head is ATP binds the ATP binding site on the myosin head and causes myosin to release the actin. And the rest of the myosin head returns to its cocked position. And then this right now is an uncontracted sacromere. But when a sacromere goes to contraction, the A band don't change their length at all, but they start to move in, and as they're moving in, the I band and the H zone shorten and causing the Z lines to come closer together. And then the M line pulls in, making the contraction of the sacromere.